Hi Algebra 1 students, this is Miss Graham, and today we are going to get started looking at how we can model quadratic functions from a graph. So we're going to be doing a modified version of the Springboard notes. So I have kind of this link on our calendar for every day of the modified textbook, which is this document that I have up here, which we take snippets of different pieces of the textbook and apply them together. So we're going to start looking out at section 29.1, modeling with a quadratic function. If you haven't already yet, go ahead and download this from our calendar. So our learning targets for today are we're going to model a real-world situation with a quadratic function. We're going to identify quadratic functions, and we're going to write a quadratic function in standard form. So let's go ahead and read our background story problem. So Coach Wentworth coaches girls soccer and teaches algebra. Soccer season is starting, and she needs to mark the field by chalking the touch lines and goal lines for the soccer field. Coach Wentworth can mark 320 yards for the total length of all touch lines and goal lines combined. She would like to mark the field with the largest possible area. As we can see, I have the picture that we're going to be visualizing right here with our goal lines and our touch lines. So it says FIFA regulations require that all soccer fields be rectangular in shape. So our first question is, how is the perimeter of a rectangle determined? How is the area of a rectangle determined? As a reminder, the perimeter of a rectangle is found by adding the lengths of the four sides. So we're going to say the perimeter is found by adding the four sides. And then for our area, we can find that by multiplying the length times the width. So we will multiply length and width. All right. Let's keep going. We're going to scoot on over to the right so we can see number 2 here. And if we scroll down, we're going to be looking at this table. Whoop, this table right here. Sorry about that. So let's go ahead and read what that question has to say. It says, complete the table below for rectangles with the given side lengths. The first row is completed for you. So looking at this, we can see that our first column on the left side is the length in yards, and then we have the width in yards as the second column. So we can see altogether for our lengths, we have 10 and 10 on each side. And we started off with an example of 150 on the two widths. So think about this. If we added 150, that's 300. Then we added 10 and 10, that's 20. So we get a total of 320 as our total perimeter. Now we're going to do a couple of these together, and then I want you to pause the video and see if you can finish some of the rest. So let's start off looking at our next example. If our lengths are 20, that means we have 20 and 20, which is 40. So we know the remaining amount. So 320 minus 40, all right, so that's going to be 280. We want to divide that by 2 because we want to find the width. So 280 divided by 2, that's going to give us 140. So we know each side of our width is going to be 140. Let's go ahead and try another one. Again, we're given that each length is 40 on each side, so altogether 2 lengths will be 80. If we subtract that from our total here, we get 240. And if we divide 240 in half so we can figure out each width, we get 120. So I want you to go ahead and pause the video right now and see if you can fill the rest of these in. All right, let's go ahead and check. See if you got the rest of them filled in correctly. You can see as the length tends to increase, we know the width tends to decrease. We can see that's how we make up a rectangle. If one side is bigger than the other has to be smaller. Or if one side is smaller than the other side has to be bigger. So this is a fun one down here. Think about this. If I have a length of L yards, what could I do to find the width? So talk about the process, kind of what we were thinking about out loud, right? We subtract 2 of these from our total, right? And then we want to figure out how to take half of that, right? That's kind of our ultimate goal. So think about this. We have 320, and we want to subtract 2 of the lengths. And then for our result, we want to divide that by 2 because we only want 1 of the widths. So think about this. We have 2 pieces in our numerator. We're dividing by 2, so we can actually divide each of those terms by 2. So the way we can rewrite that is 320 divided by 2, well, that's 160. And then we're subtracting, well, 2 divided by 2 is just 1, so we're subtracting L. So that's one way that we can write the width if we have a length of L. Now, you're probably thinking, what does this connection have with quadratics? Do not worry, we're going to be working up to that. Let's look at our third column next. Again, we know we have the total perimeter is the same. We know that cannot change since we said, hey, we can mark 320 yards for the total length. That will stay consistent. But now let's look at our areas. Remember, perimeter is different from area. Perimeter is adding all the four sides together. And then for area, we're looking at the space inside. That's two-dimensional. And we're saying, well, will it be the same like perimeter? Maybe it will be different. So let's think about this. Remember, area is found by multiplying the length and the width. So we're going to multiply 20 times 140. So when we do that, we actually get 2,800. It's different from our first example, and we can see the area increased. So I want you to go ahead and multiply the length and the width for each of these and see if you notice a pattern. Go ahead and pause the video right here. All right, let's go ahead and check our results. So go ahead and check your numbers right here. And you're gonna see that it's kind of cool. We see there's kind of mirrored answers, but that actually makes sense because if we have a length of 10 and a width of 150 and we flip-flop it, now we have a width of 10 and a length of 150, it makes sense that they're gonna have the same area. We're multiplying the two same numbers together, just different length and width. Now, it's cool because we can see the numbers tend to go up, reach this highest point right here, and then they tend to go back down, mirroring each other. So think about maybe what this would look like on a graph if we were to graph it. Now, the fun one is the one down here. So we know we take the two results and multiply them, so we would take our length of L and multiply it by 160 minus L. That's our width. Now, keep in mind, right, we are usually only used to working with two variables. And that's why we wrote this here. We wrote the width in terms of length. So we're only working with the letter L to get our area. So we talked about quite a couple of patterns that we saw right here. And that's actually what number 3 is going to be asking. It says, describe any patterns that we observe in the table. So I'm going to have you pause the video right here and see if you can write down any patterns that you observe. And then we're going to compare to see if we have some of the similar findings. All right, let's talk about some of these patterns that I noticed. So I saw that as our length increased, right, we know our width decreases. We kind of talked about that pattern before. And vice versa, as the width, maybe that increases going up this way, then that means the length will decrease. I also noticed that as our length is increasing, we see that our area increases, but then it reaches a maximum point and then it decreases. I also saw that our greatest area, and I'm going to highlight it right here. So our greatest area was when we had both the length and the width at 80 yards. So maybe there's some idea of a square yielding our maximum area that we're going to talk about and get to. All right, let's go ahead and move on to numbers 4 and 5. Number 4 says, is a 70-yard by 90-yard rectangle the same as a 90-yard by 70-yard rectangle? Explain your reasoning. So I want you to think about what we've talked about already, and I want you to see if you can answer this question. Play the video when you're done. All right, so just like we talked about before, we know that the two rectangles will be the same. We just have different orientations. So I kind of drew a picture for us. If we have one side times the other and it's the same numbers, maybe it's just turned in a different direction, but they will end up having that exact same area. Okay, cool. Looking at number 5 now, we're going to do a really fun part of this lesson. So it wants us to graph the data from our table above. So we got to go up above, maybe look at it above right up here. And then we're gonna, use some of these columns as ordered pairs. So let's look down at our graph here. And we're gonna see kind of our x-axis, right, is actually going to be the length. So we're gonna put our lengths, I'm gonna call L, as our x-axis. And we can see they go up by increments of 20. And then if we look at our vertical axis, our y-axis, we can see it's going to be the area of our rectangle. So we're looking at the yards squared. So at the top, I'm going to put A to represent area. So that way we know what we're going to be comparing. If it helps you on out, let's go up and find those two columns that we're going to be looking at here and actually graphing, putting them as ordered pairs. So we first want our input to be length. So that's going to be our first column here. And you can see this bottom result. We're actually not going to graph that, so we're just going to look at the top number result. And then we're going to compare that to our areas. So we have our areas right here. So we're going to read across. So we're going to have 10 be our input, kind of like our x value, and our output is going to be 1500, our y value. And we can see on our table, we can see on our graph here that there are values that go up and high. So I will plot this first point with you. We're going to plot 10 and 1500 together. So let's go ahead. We're going to find 10 on my x-axis, so that's about halfway between 0 and 20. And then what we're going to do after that is we're going to go up to 1500, 1500. So that's between 1000 and 2000. So I'm going to go ahead and graph my point. I'm going to put it right here. So let's go ahead and plot that point right between 0 and 20 on our x-axis, and right between 1000 and 2000 on our y-axis. So I want you to go ahead, pause the video. You are now going to go ahead and graph all of the points, and then we're going to compare shapes and see what we get. So go ahead and pause the video here. All right, let's go ahead and check our results with each other. So you can see I started plotting the points. We know that they increase in length and area. They kind of come to this top point, this maximum, and then as the length increases, the area decreases. It actually kind of looks a little like a mirror. Like, think about this. If I folded this right in half, kind of along this middle line right here, we know that each of these points would probably overlap and be on top of each other. So we're going to learn about, this line that kind of divides this shape in half. And what's really cool is if we actually, connected the points in the future. I know I kind of did that a little badly, but if we connected them, they actually create the shape called a parabola, which is a curve. Now, we're not going to connect them here. We're just going to leave them as points because we didn't always find the lengths in between. And the purpose of us connecting the points means, okay, we found lengths of all rectangles that were in between here. We didn't from our table, so that's why we only plotted what we found in the table. So keep that in mind as a reference when we should connect the points and when we should not. We're going to go ahead and go on to the next page. As you can see, we are going to be looking at a couple of problems. We're going to be looking at numbers 6 through 10. So let's go ahead and zoom in, start looking at 6 and 7. And it also might be a good idea to kind of have our graph and our previous table from numbers 5 and 2 on hand so we can kind of answer these questions while using those. So number 6 says, use the table and the graph to explain why the data. And number 2 and 5, why is this not linear? So why is this not a linear relationship? So think back to what linear means. Have any ideas? Well, linear means there's a constant rate of change. Every time we go up a certain amount for our x value, the y value increases in that same increment. Right? We also know the points have to lie on a straight line in order for it to be linear. So really we have to look at two ways to distinguish that this is not linear, from a table and from a graph. So from the table perspective, right, we know it's not linear because there's no constant rate of change. So we're going to say no constant rate of change. And then we know from our graph that the data is not linear because the points don't lie on a line. So points don't lie on a line. So that idea of linear relationships is going to come back, and we're going to compare this relationship to it. So let's look at number 7 now. Now, just like we did with the table, just like we did when we were looking at, number 3, we described any patterns that we observed. I want you to do the same for our graph. So go ahead, pause the video here. I really want you to see if you can notice any patterns in the graph on our previous page. So 2 points that I may note of are, as the length increases, the area increases, but then it reaches a maximum and decreases. So that's very similar to what we saw on the table. And something else that we notice is there is symmetry about that line that goes through kind of that middle, that maximum point. Now, if it's a vertical line, it's usually written in x equals that number that it lines up with. But in this case, since our input wasn't x, it was L, I wrote it as L equals 80. You could have said a couple of more things, but those were kind of 2 of the big ideas that I saw that maybe we haven't pointed out just yet. Let's go ahead and look at number 8. All right. So number 8 says, what appears to be the largest area from the data in items 2 and 5? So it's asking us to look at the table, look at the graph. What do you think is the largest area? So go ahead, check those out, and write down what you think that is. So did you see the largest area is actually going to be 6,400 yards squared? Or if you said square yards, that's totally fine. And we see that this occurs when the length and width are 80 yards. So maybe we're going to notice some type of relationship that maybe the biggest area is when our width equals our length, when those 2 numbers are the exact same. So now let's look at number 9. Number 9 is a little bit tougher, so I'm going to help you out with this one. It says write a function a of L that represents the area of the rectangle whose length is L and whose perimeter is 320. So remember, we're saying A of L. That's going to be our area. So it's similar to writing f of x when we were looking at that specialized notation before. If we were given x, right? We had an input and an output. That's what this is similar to. We're now saying, okay, instead of writing x, we're going to write L. And instead of writing f of x, we're going to write A of L. So just like using x and y, right, we're going to have an input and we're going to have an output. Let's first try thinking about this from the lens of our table. So think back to what you saw in our table. If we knew our length was L, what do you think the width was? What did we write down what the width was? We wrote down that the width was 160 minus L. So we know we have to multiply those 2 results together to get our area. So if we take L and we multiply it times, let's try that again, and multiply it times our 160 minus L, right, that's going to equal our area, A of L. So that's our function that we're looking for. That's our equation that we want to write it as. And we know its perimeter is still going to be 320 because those were the only examples that we were looking at. So again, you're probably asking me, Miss Graham, what does this have to do with quadratics? How does this connect to what we just learned about? Well, here's where it's all going to start to come together. Right here it says the function A of L. It is, right, a quadratic function. What? You're like, wait a minute, how is this a quadratic function? Well, think about this. The greatest degree of any term is 2. So we're looking for an x squared. Or maybe if we go back up to our equation, we're looking for an L squared. Well, so far I don't see an L squared here. But you know what I could do? I actually could probably distribute and multiply that L out. So that way I would get 160L minus L times L. Well, remember, when we multiply like bases, we add the exponents. So that's L squared. That makes sense now. This is a quadratic. We just wrote L squared, right? We had L squared here. Now keep in mind, the standard form of our quadratic function, right? This equation. We've seen this before. It's y equals ax squared plus bx plus c. You've seen that before. Or maybe instead of y, you've seen f of x in that spot. We know that a, b, and c are real numbers, and a cannot be equal to 0. That means the coefficient of a is not 0. So let's say we wanted to put that in standard form, right? We could put L squared first. Technically, it's a negative, so we have to make sure the negative goes with it, a negative 1L squared. And then we add 160L, and we can see there's no C value. Our negative 1 is our A value, 160 is our B value, and there's no C value. So this idea, what we just graphed, what we started coming up with, this relationship is going to relate to quadratics. So I know I might have already helped you out a little bit with number 10. Maybe I already did it for you, but if you're listening, this should be pretty easy. So I want you to go ahead and write this function in standard form, the one that we just came up with above, and write out what the values of A, B, and C are. So go ahead, pause the video, see if you can do that. So again, if you were listening to me before, right up here, I actually already wrote it in standard form for you. So we have A of L equals negative L squared plus 160L. So keep in mind, that's our standard form. And our A, B, and C values, let's write them down. So our A value is negative 1, our B value is 160, and our C value, remember, that's going to be 0 because it's just like saying plus 0. All right, so we are actually done with our notes for today. I know, right? We kind of were experimenting and exploring, what are really quadratic equations when they're graphed? What are they gonna look like? And then later on this week, starting tomorrow and the next day, we're gonna start actually analyzing, maybe how does the equation connect with the graph? We're gonna start graphing it ourselves, so get excited for this. Woohoo! Well, as you can see, it's very important that you are an active note taker as we are going through these notes. So what you are actually going to have to do before being done with class today is you are going to have to submit your lesson notes from this video lesson, 29.1. That's right. It's pretty important to make sure that you are writing down and taking notes and are actively participating as I'm going through the lesson. So these are going to be kind of our last couple of homework assignments as we finish up the year in the next 2 weeks. So definitely make sure you're keeping up with this. And if you didn't get everything written down, go back to the video lesson and catch up where you need to. We're going to check in tomorrow, move on to start looking at graphing and analyzing these quadratic functions, and we're going to do a little practice. So I will see you then.